Okay, let's get started. So welcome everyone to the afternoon session on type-driven runtimes. I'm Ningning Xie. I work for the University of Toronto, and we have 4 exciting talks in this session. And our first talk would be given by Daniel about semantic encapsulation using linking types.
Thank you. So this is joint work with Andrew Wagner and Amal Ahmed at Northeastern. So I guess the first thing I want to address is why are we doing this? Why have we been doing this? We've sort of been banging our head against this problem for a while. And essentially, there's a problem, which is that people come up with all sorts of nice type systems. They come up with really expressive, interesting ways of reasoning about programs, maybe ruling out all sorts of classes of bugs. Maybe they even prove things about those type systems. Maybe they publish papers. And so we end up with all this nice stuff over here. And then if the language actually gets in front of anyone, and anyone starts writing programs in it, it's sort of inevitable that we just punch a big hole in the bottom and say, well, sort of for practical reasons, we need an FFI, or we need to be able to link against C code, or we need some sort of features in order to implement parts of the runtime, or this and that and the other. And this makes sense. Sort of there's an incredible amount of expressive power in these low-level languages. But the problem is that if you stare at this and think about this for a little while, you realize that it means that type checkers, type systems in sort of our flagship examples of type languages are a little bit closer to linters, right? They give us errors, they help us, find bugs, but they only do that to the extent that we're not using these features that sort of render those theorems completely useless, okay? And certain types of programs use more or less of that. And depending on how well tested that code is, right, you can trust it more or less. But that's all sort of, those are a lot of caveats, okay? And so the question really is, can we do better, right? And obviously, I think the answer is yes, and that's what I want to talk about today. Sorry. So the main idea, which is not that clever, it's sort of obvious, is we should model this behavior. We shouldn't ignore it, right? We should say, if we're going to bring in code from C, if we're going to bring in low-level memory manipulation, if that's important, we should actually model this. We shouldn't just pretend it doesn't exist when we actually are proving things. And it's not that people haven't been doing that, right? People have been studying untyped languages. People have been studying effects, state, control effects, all sorts of stuff, basically as long as we've been studying any of this stuff, right? This is very well understood material. The problem is that if you take your nice sound language that has really rich reasoning principles, and then you bring in the semantics of C, and you do that naively, suddenly all your types are the same. Your types sort of have no meaning because C has sort of polluted everything. So the problem is not actually modeling sort of challenging behavior and sort of expressive behavior. The problem is encapsulation. How do you bring in this expressive behavior that you're going to need without sort of letting it destroy everything else, right? And so one observation that drives a lot of this, or maybe how we started making sense of some of it, is that encapsulation, or really that interoperability, happens after some kind of compilation, typically. Okay, and there are ways that this gets more complicated. But basically, if you take a language like OCaml, and I don't mean to pick on OCaml, it's just an example, and C, which I will pick on, there is no sort of OCaml interpreter and C interpreter that model the operational semantics of these two languages where you bounce between those when you're making foreign calls. It doesn't actually exist, right? We can write it down on paper, but what actually happens is that both get compiled down, and like I said, there are more complicated versions of this picture. This is one of them, right? That they can get compiled down into some common target. There's some place where there actually are calls going back and forth. At some point, control has to switch from a stack of code that came from this language to a stack of code that came from this language, right? At this point, we have some commonality, and this is the point where we're actually bouncing between languages. And so this is the point where we sort of have to at least pay attention a little bit, pay a little bit of focus there. So here's the idea. We should model foreign behavior. So when we import foreign code, we want to give types to that. And so I say novel linking types, not novel as in research novels. Novel as in not in your language already. So the whole idea was you came up with very sort of rich, expressive types that were sound and didn't include maybe low-level memory manipulation. You should give yourself a way of describing that behavior soundly, right? Don't say, well, pointers are kind of like numbers, so we'll just use integers for that, okay? That's not sound, okay? Give yourself accurate types, and then figure out how to encapsulate the code that uses those new types from the rest of the program. So easier said than done, maybe. But this is, if you look at the descriptions look at the documentation in the Haskell FFI or the Camel FFI, this is actually what people describe that you should do, right? Be careful, use these tools sparingly, and then ideally wrap up the nastiness in a safe sort of interface and present that to the rest of the program, right? And like Rust makes this explicit, right? There's an idea, there's a whole language mechanism saying, here's the unsafe part, here's a safe part. Ideally, you only present safe APIs using the safe part. So how can we make this be sort of more explicit so we can make it be more formal? Essentially, first we need actual types. So if this blue language is my core language, then I need to extend the types to somehow express whatever behavior I'm trying to link with. So for example, if I had a pure simply typed lambda calculus with integers as a base type, and I wanted to bring in code that throws exceptions, okay? And there's classic little examples of how this causes weird reentrant behavior if you just allow those functions to flow into the normal types. So we don't want to do that. Instead, we want to split that arrow type into two, okay? Introduce this modality to say, well, there are pure types, that's what we had before, but now there's these weird arrows that might throw exceptions when you call them, okay? We need to connect these new types to our original types. We do this with two typable functions. Lift maps core types to linking types. This sort of makes real the idea that it is an extension, right? Technically, you might be editing things, adding things, removing things, but we want any existing type to be able to be expressed in this new type system. This is really practically important because I don't want to take any program. If I have any program that type checked, it better still type check, right? Also, I don't want to have to, if you can infer type on this, I'd like to be able to keep using that inference and then just lift it up. Lower is more interesting because this is how we're actually going to implement encapsulation. And so this part on the screen should hopefully look a little suspicious because I'm saying, well, we're just going to take this arrow that can throw exceptions and we'll treat it as a pure arrow. We're actually mapping both functions back to our normal function type. And so the way that we're going to make sense of that is to step back and think about, well, what do we mean by encapsulation? Well, encapsulation has to happen at the level of the target, okay? So our targets are oftentimes expressive not only in terms of what they can allow you to do, but also what they can allow you to control, right? And so in the case of exceptions, so what I want is for every type, every extended type, I want a little bit of code that I'm writing with these little squiggles that when wrapped makes this behave like the lower type. It wraps it up, packages it up, and says this is now working like encapsulated version. So for exceptions, it just catches them all. It's not complicated, right? This is just it expanded the function, and we run this, and we catch all exceptions. And there's some details, obviously, there. Everything that's on the slides is simplified for the sake of the slides. There are other ways of doing this. This is the dynamic enforcement version. There's a way of doing this statically, where you basically, per expression, have to prove that this expression behaves like that. This is what Rust Belt did. Okay? They showed, oh, this does weird stuff inside, but actually it behaves as this core type. Okay? The reason for presenting this dynamic version is that it allows us to provide this sort of friendly to the programmer interface, which is saying make explicit the encapsulation boundary. You write in the yellow, the orange language, all the code that involves the FFI, right? It involves making calls, maybe to C or whatever else. And then at some point you say, okay, this is my block that should be safe. So I'd like to be able to use that from the rest of my type system, rest of my language. So wrap it in these boundaries. And then in order for this rule to work, we just insert this in compilation. Okay? Now I've said that this, I've been gesturing at soundness or how to prove this. If you actually want to do this, most of it relies upon an idea, an old idea, not that old, but Nick Benton was working on, had a series of papers about 15 years ago where he started trying to figure out this realizability idea, which these models, they're logical relations that are inhabited, they're indexed by source types. So in this case, the blue language or the yellow language, but they're inhabited by target terms. So what you're saying is, how do I give meaning to, for example, a Boolean or an integer, source concepts, as these are unary models of sets of target terms. So in my target, maybe I don't have true and false, but I have 0 and 1. I can encode Booleans that way. So that's the meaning of Boolean. Integers are integers. And so this realizability model, we realized, a couple years ago, that this actually becomes really, really useful when you're thinking about interoperability, much more so than it maybe was when Benton was proving soundness of single languages. And the reason why that is that it allows you to ask direct questions about interoperability. Like, is this type in one language or in an extended version of the language the same as in another language? Normally, this is kind of it's a bizarre thing to do unless you've already moved into a model where you have some commonality, right? If you're thinking in terms of the source, the syntax and the operational semantics of the source, these are not really comparable, right? But because the substance of the models are the same, it allows us to do this. And more importantly for this talk, there's a version of this, sort of simplified version of this that answers other questions that we had at PLDI last year. We can ask, what can we put around values from this extended language, the linking code, that make it behave as the core code? How do we actually encapsulate, right? And this is actually sort of sensible to do because all of this stuff is just target code, right? It's all happening in the context of the target. So in particular, we can prove that those lift and lower functions, type level functions, do what they should do, right? For lift to be sound, we want to know that if any value is in the relation, is a value of type, the core type, then it's also a lifted type. That's what we mean by when I said lift must take types to the same type. Right? This is a very formal notion. They are the same. This goes both ways. Okay? They have the exact same meaning. We give meaning to the types by building these models, and then we say these are actually equivalent. Okay? Lower is the more important thing, which is saying if we have an expression, target level expression, that has type, yellow type, then if we wrap this code around it, encapsulation code, it should behave as this core type, right? Encapsulation should actually do what it's supposed to do, okay? And this ends up being a little bit trickier if you think about it, because the whole point of having this extended language, in the example that I have for the talk, it can throw exceptions. Okay, so this might throw. This is supposed to catch it, but we're supposed to prove that throwing followed by catching behaves like whatever the resulting type is in this model. Well, this model was intentionally designed without thinking about exceptions, right? The blue language doesn't know about exceptions. There's not even anything about exceptions. Building models for exceptions, usually there's some kind of continuation relation. There's a lot of stuff about exceptional control flow. How do we take something that does that and prove that that works? Well, it turns out we have to sort of split it into steps where we first show that wrapping it is in the lifted version of that lowered type, because this gives us enough logical structure to actually prove that encapsulation works, because we have whatever additional stuff that possibly exists in these yellow types. And then once we have that, we can use lift soundness to just remove that up arrow. And obviously, all the details of this are in the paper or are in the technical report. A lot of things are simplified here. If you're familiar with logical relations, you're probably confused as to why there's no sort of logical state along with the terms, and that's just for simplified presentation. Once we do that, we have to prove soundness of the whole language. This is completely standard for semantic type soundness. We prove that typing rules imply corresponding implications in terms of the model. What that gives us, once we prove that the libraries we're linking with actually satisfy the types we care about, is an actual soundness proof that includes linking with genuine target code, right, that could not have been expressed in your source language, right? And I have an example here, or I'll show you this first. Sort of wrapping up. We split this, so I said that this was an idea, something that I'd like people to do. I've split this intentionally into sort of two halves. There's an implementation here, there's an idea for an implementation, and then there's an idea for a proof, okay? The implementation half is what you, if you are implementing a language that has an FFI, could do that I think would actually make things better in terms of programmers being able to reason about things, okay? That's the first three steps of what I showed you, right? The most important part here, right, is actually try to engage with what are the features you actually want to bring into your language, right? Rather than just sort of punting on it and say, well, we'll just let in anything from C or anything from assembly or whatever it is. Try to actually figure out what are these features that we don't have in our language that maybe for good reason we don't want to bring in because they make things really hard to reason about. Maybe suddenly your language includes weird modal effects, right? And you don't want actually to put that on most of your programmers. But you can for the people who are actually dealing with sort of writing this low-level code, right? So try to actually figure that out, right? Then define how that weird type system relates to the normal type system, right? And figure out how to actually enforce that, right? These three things are engineering questions, okay? If you do this all right, things are sound and you're good. Obviously, hoping that it works is not usually good enough, or at least we hope you would do better. And that's the point of sort of the second half is how would we actually prove this? And we've given you a recipe for that, which is what these models allow you to do. But the reason for showing it this way is that even if you end up with a proof sketch, you're still in a very different situation than you were than most language implementations are. Because if you prove a language sound in the absence of the FFI, you're not removing a part that is maybe, you know, a detail that is irrelevant. You're removing a part that is incredibly complex, right? Whereas it's possible you could take this language and you could simplify some bits that maybe aren't super relevant, and prove some version of the simplified language, right? And so you don't have a perfect proof, but you have something a lot better than we typically do, okay? So I have an example. I'm going to skip this for time. This is in the paper. We're just one of the case studies that we have. It's a pure functional language, and then it links with a language that brings in state, and it doesn't have polymorphism. So here we're just implementing Fibonacci using a memo table. So we have a way of just writing in values, so it's not exponential. And there's another case study in the paper that brings in exceptions, which is interesting because you get weird control flow and the structures of the models become very different. And both of those compile to an untyped target language, which I think is important to sort of show this doesn't rely upon any types. Sorry. Doesn't rely upon any types at runtime, despite the session that I'm in. It's all done sort of in terms of the actual model, sort of what the operations you perform in order to witness the type invariance you want to have, rather than anything actually having to happen. So with that, I think I'm out of time. Sorry, I took a little long. Thank you.
Sure. Thank you. It's really cool work. One of the challenges with FFIs is that often it's giving you access to operations that are challenging to encapsulate.
Yep.
In particular, challenging to encapsulate in a high-level type system. And so state can be challenging to encapsulate, but even going further than that, like low-level access to memory or something like that. So can you talk a little bit about how you deal with challenging to encapsulate features?
Yeah, absolutely. So there's a question at the beginning, there's a design question at the beginning, which is this actually something your language should just be able to express natively? Because maybe the answer is yes. Maybe the problem is that your language should be able to express this effect or this feature, right? And then it's a different question, right? And so an example of something that you could not encapsulate if you didn't have it already is, writing to a file. There's not, unless you want to just virtualize the entire file system and be able to roll that back in some weird way. If you allow file writes and reads, there's no way to sort of encapsulate that if you don't have that already, right? And so probably some version of that needs to be in your understanding of how your language works, right? If you want your language to be something someone can reason about. It's if you're trying to do things that actually can be encapsulated, even if it is difficult. And I think memory manipulation is a good example where we do have type systems for low-level memory manipulation, right? This is sort of what a lot of our substructural type systems or what of our separation logics allow us to do is prove complicated things about manipulations of data structures in memory. And the goal always there is to prove that it actually satisfies some API that is safe, right? That's always the goal, right? And so the idea is, can we actually sort of realize that? And I think Rust Belt is one example of a way to do that. It involves a lot of manual proof, right? You have to prove that, this block of code does what it's supposed to do. But at that point, you're putting a manual proof at the encapsulation boundary, and then you're getting exactly what you want, right?
Right. I'm just thinking about the strategy you described, where we have some encapsulation code that you generate, and I'm thinking, how does that work in?
I mean, there's dynamic memory isolation techniques that are used as well, like the idea that you would just allocate yourself a block of memory, and then when this is done, if there are no pointers to it, you just throw it away. That's a simplified version of things, right? You could do, sometimes you want to do sort of low-level, like arena manipulation, right? And that's something you could express safely, right? If you give yourself that mechanism. I think the question of sort of how do you actually encapsulate is a really fascinating one. It's something that I think especially the security community has been spent a long time working on, and there's lots of really interesting sort of contributions there. And I sort of wished there was a little bit more effort to take some of those features, some of which are in hardware now. You know, people have varying opinions on how nice those abstractions are, but like, can we use some of those to then give us sort of interesting semantic guarantees on the other side? So.
Yeah, thanks for the discussion. Due to time constraints, let's leave the rest of the discussion as well as any further questions offline. And